Right, looking at a second example now of projectile motion. This time where we're dealing with a situation where the motion is a complete parabola rather than being the half the parabola that we dealt with in the first example. There is extra information available in this problem that we don't necessarily initially identify, and that is that at the top of the motion over here, in terms of the vertical direction, the velocity is 0 meters per second. There's still a horizontal velocity, but there's 0 vertical velocity. So using the symmetry of the problem, this can help us be able to work things out. So what have we got? A cannon fires a shell at 100 meters per second. Now, a lot of the stuff to do with projectile motion was developed in the time of Galileo, and you might think, well, why was that? And let's face it, the reason was military. I've been to a museum in Florence, science museum there, and there's all sorts of calculating instruments and so on for figuring out the range of artillery or cannon shells and that sort of thing. If you aim the cannon at a certain altitude and you fire at a certain velocity, that sort of thing. So yeah, I mean, these things were driven originally by, I think, a military type application. All right, so we're going to assume negligible effects of air resistance, which may, or to be honest, may not really be true. We've got the thing fired at an angle of 35 degrees with a velocity of 100 meters per second. In answering this first part, we hark back to our first topic where we looked at vector components, and what we're being asked for here is to work out the horizontal component of that velocity and the vertical component of the velocity. The vertical one, first of all, let's call it Vy, and let's call that let's call that one Vx. Right, pen stopped working for a moment there for some wacky reason. All right, so Vy is the side that's separated from the angle, so therefore that is 100 sine 35 degrees. And this one, Vx, is the side that's connected to the angle, so it's 100 cos 35 degrees. All right, and we're going to be using those two pieces of information to work out or in further calculations. So 100 sine 35, 57.4. And that's going to be meters per second. 100 cos 35, 81.9. All right, we've got to remember that this horizontal component doesn't change throughout the path. The vertical component starts off being vertically upwards, and that decreases until it becomes 0 at the top, and then on the other side it becomes the same component downwards effectively. There is a symmetry to the motion. Right, let's move on to part B of the question. I'm probably going to need to try to remember those two numbers, 57.4 and 81.9. I'm just going to write them down here. 57.4, 81.9, so I don't forget those two numbers. All right, the height to which the shell rises. Now, whether the shell is doing that or whether the shell is doing that, it makes no difference to the calculation. All right, so we've already looked at examples where things go up and down. This time is going up and down, but with the sideways motion superimposed. So really, we just need to consider what's happening in the vertical plane. All right, and what we do is we break the thing in half and look at half the motion only. All right, so let's see, what do we got then? We've got the vertical velocity, let's call it u, the initial vertical velocity, u, y, and we work that out over here, I think, to be 57.4 meters per second. The velocity at the top, so Vy, is 0. Now, because I've called u, which is upwards, I've called that positive velocity. then acceleration, which is downwards, I'm going to have to call negative. So acceleration equals negative 9.81 meters per second squared. And what are we trying to find? S, the vertical distance to which the thing rises. And since that's upwards, I think that should come out to be a positive value. All right, so no time in this one. So we're looking at V squared equals U squared plus 2AS. All right, so 0 squared equals 57.4 squared plus negative 9.81 S. All right, so 9.81 S, bringing that over this side and making it positive, equals 57.4 squared, which is 3295, just rounding it marginally. So S in that vertical direction, 3295 divided by 9.81 comes out to be 335.8. So let's make it 336 meters. So it rises 336 meters in the air. All right, the time taken for the shell to reach the target at ground level. Right, so again, symmetrical motion. Calculate the time to the top and then double it because it takes the same time to head back down again. All right, so for this particular one, I think we should be able to use, let's think about this. We want time. Well, you could use S equals U plus V over 2 times T. That's probably the easiest calculation to do. What do we figure out S to be? We figured out S to be 336. So 336 equals the average of, going back again and reminding myself, 57.4 plus 0, all divided by 2. That's the average velocity times the time. So 336 equals half of 57.4, 28.7. I should have done that in my head. T, so T equals 336 divided by 28.7. 11.7 seconds. So therefore, don't stop at that point. Time for the whole flight, time to reach target, if you like, equals 2 times that. 2 times 11.7 equals 23.4 seconds. All right, and the range of the shell, oh, that one's just the horizontal motion, so S equals V times T. We've just figured out that the time is, what was it, 23.4 seconds. And the velocity was that horizontal velocity component from back in part A, which was 81.9. And you can figure out the answer to that.